Hi Year 11 and welcome to our very first lesson for calculus. In this topic we're going to cover the derivative, properties of curves, rules of differentiation and rates of change. Now central to the study of calculus is the concept of a limit, and in mathematical terms the limit is the value that a function approaches but cannot exceed. So think of it like a brick wall or a ceiling. Now there's this famous mathematical joke, and it says, an infinite number of mathematicians walk into a bar. The first one orders a beer. The second one orders half a beer. The third one orders a quarter of a beer. And the barman says, you're all idiots, and pours 2 beers. Now that might not make much sense to you, but have a look at this. Suppose this is a beer. And this would be half a beer. This is a quarter, an eighth, a 16th, a 32nd. Can you see how it's getting closer and closer to filling up this beer? And the limit is 2 beers. In other words, we can't get any more than that. We'll never actually get to 2 beers, but we'll get ever closer and closer and closer. Now here's the notation for limits. This says, what is the value of 3x minus 1 as x approaches 1? We can see this graphically. This is the line y equals 3x minus 1. You can see that the gradient is 3 over 1. The y-intercept is negative 1. What is the value of 3x minus 1? That means what's the y value as x approaches 1? So as the point is moving up here and getting closer and closer to x equals 1, what is y approaching? Well, it's approaching 2. Now all we do is substitute the 1 in. So 3 times 1, take away 1, is 2. Now remember back when we were learning about functions, we talked about continuous graphs. A graph is continuous if it has no gaps or jumps. So let's consider this piecewise relation. F of x is equal to 2x plus 1 when x is less than 1, and x plus 1 when x is greater than or equal to 1. And if we graph it, it looks like this. So is this a continuous graph? No, it has a jump in it. Is it a function? Yes, it is a function. It's going to pass the vertical line test. The only part that it might have an issue with is here, and at this point, x is equal to 1, it's equal to 4, not 3. So it is a function. But will it have a limit at x is equal to 1? And the way to tell that is to see whether we get the same number when we go up this line as we get when we come down here. So as my point is moving up, 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 up here, getting closer to x is equal to 1, the limit is 3. But here, as my point's moving down, 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 getting closer to x is equal to 1, the limit is 4. So no, this has no limit. Let's try a harder limit. What is the limit as x approaches 2 of x squared minus 4 all over x minus 2? Well, what happens if we substitute in 2 for x? We get 2 squared take away 4 on top, and 2 take away 2 on the bottom, which is 0 divided by 0. And this is undefined. We can't ever divide by 0, even when it's 0 on the numerator. So what can we do? Well, I can see that x squared minus 4 on the numerator, and I can factorize that. It's the difference of 2 squares. So x squared minus 4 is equal to x minus 2, x plus 2. And then can you see that those x minus 2's cancel out? And so I'm left with the limit as x approaches 2 of x plus 2. And now I can substitute in without any problems. The 2 just goes in where the x is. And so the limit of this expression is 4. Now what do you think this looks like? Looks like some sort of parabola thing, doesn't it? It's actually a straight line, which might surprise you. It's actually y is equal to x plus 2, the straight line, except it has a hole in it. It's not defined when x is equal to 2. But have a look at the limit. As x gets closer and closer to 2, the line gets closer and closer to 4, and that's from both directions. So the limit is 4. Okay, now that we have that concept of a limit, understood, or hopefully we do, we can start our real exploration of calculus or differentiation. We're going to start with gradient. Recall that we can calculate the gradient of a line through 2 points, x1, y1, and x2, y2, using the gradient formula. So if our points are 2, 4, and 1, 1, we can just substitute those values in, and we're going to end up with 3 over 1, or 3. So the gradient, we call this line a secant that cuts in 2 places. The gradient of this secant, AB, is 3. Let's consider the curve y equals x squared, that's this black curve here, and the point 1, 1 that lies on the curve. What is the gradient of the tangent to the curve at this point, 1, 1? Now, a tangent is a line that just touches a curve in one position. So we want to find the gradient at this point. Now, here's the thing. We can't use the gradient formula because we only have 1 point. We'll end up with 0 over 0. Remember, that's undefined. So we're going to start with our secant. So remember, that's a line that cuts a curve in 2 places, and we've calculated the gradient. Here it is 3.841, and we're going to slide this point down the curve until it approaches this point here. So that blue line there is going to go from being a secant into a tangent. Let's have a look what happens. So currently it's 3.841. Slide it down, and you can see that gradient getting less steep. There it's 2.9, getting closer and closer, 2.5. Now what happens when it becomes exactly the same point? It's undefined. Here's a table of those gradients. So we started around about 0.24, and the gradient of the secant through 2, 4, and 1, 1 was 3. Then as we went closer, say x is equal to 1.5, the gradient was 2.5, and then 1.1, we're getting closer to 1, aren't we? The gradient is 2.1. Now, if I say the x-coordinate is 1.01, the gradient is 2.01, and at x is equal to 1.001, I have a gradient of 2.001. So what do you suppose is the limit? Because remember, if we get to exactly 1, our gradient is going to be undefined because we've only got 1 point. But what do you think these gradients are approaching? How about 2? So let's see if we're right. We're going to choose 2 points. We have got x, f of x, and then we've got x plus h and f of x plus h. And h is a small number. The gradient of the line between these 2 points is going to be the difference in the y values. So f of x plus h take away f of x, all over the difference in the x values, which is x plus h take away x. And I can tidy up this denominator, and I end up with this. This is actually called the difference quotient. Now, as this point slides down the curve closer and closer and closer towards this one, in other words, as h tends towards 0, this point here is going to become x, f of x, the same point. This part here is the gradient of the secant. Now, as h tends towards 0, we're going to end up with the gradient of the tangent. Now, we call this the derivative, and that's the formula for the derivative. So let's return to our question from before. We had the curve f of x is equal to x squared and the point 1, 1, which lay on the curve. And we wanted to find the gradient of the tangent at that point. So now let's use our formula we just derived. Do you remember what this means? It means substitute x plus h in wherever you see an x. So after substitution, we're going to end up with, instead of x, we'll have x plus h all squared. Take away f of x, which is just x squared. Expand this out. This is x squared plus 2 times x times h plus h squared. Take away x squared. Make sure that makes sense to you. We can cancel these x squared terms and end up with this. Factorize h. out of the numerator, those h's will cancel out. And now I can substitute my 0 in because I've got rid of the denominator. Now, let's just pause there for a second. Couldn't substitute in h equals 0 here, or here, or here because I have an h on the denominator. But as soon as I've gotten rid of the h, I can substitute in. So the limit as h approaches 0 of 2x plus h is 2x. Now this is the gradient of all the tangents to the curve f of x is equal to x squared. So what does that mean? Well, this is the gradient of all the tangents to this curve. We want the tangent at x equals 1. All we have to do is substitute it in. So 2 times 1 is 2. So the gradient of the tangent to the curve f of x equals x squared at the point 1, 1 is 2. Guess what? We were right. Now just a bit of notation and language. When we find the derivative or the gradient of the tangent, we say we are differentiating y with respect to x. And there's a couple of different ways we can write this. We can write y with an apostrophe after it, and we say y dashed. Or we can say f dashed of x. Or we can say dy dx. Now this notation here comes from this, delta y over delta x. And delta in mathematics is the symbol for change. So this literally means, how is y changing as x is changing? Now everything that we just went through, working out the derivative, we did by first principles. And that's where we used that formula, that limit as h approaches 0 of f of x plus h, take away f of x all over h. That's quite a long process. So we're going to learn now the power rule, which is a shortcut. So I'm going to tell you that if our function is y is equal to x squared, we worked this one out, the derivative, y dashed, is 2x. And you'll have to trust me on this one. Y is equal to x cubed, the derivative is 3x squared. If it's x to the power of 4, the derivative is 4x cubed. With x to the power of 5, it is 5x to the power of 4. I'm hoping you can see the pattern. What do you think the derivative of x to the power of 6 is? Hopefully you said 6x to the power of 5. And here's our power rule. If y is equal to x to the power of n, the derivative is y dashed is equal to n multiplied by x to the n minus 1. In other words, the power comes down and then we reduce the power by 1. Now, you don't have to take my word for it. You could go and work out all of those by yourself by first principles. However, you will be expanding x plus h to the power of 6, which is a lot of algebra. Now we've got a couple of rules of differentiation, so I'm going to go through those and then try and draw this all together by the end of the video. The first one is, any coefficient will be multiplied by the power when it comes down the front. So suppose we want to differentiate 6x cubed. Now have a look at this notation. This means find the derivative with respect to x of 6x cubed. So it's a nice shorthand way of writing dy dx. Okay, the 3 comes down, multiplies by the 6 and gives us 18. X, drop the power by 1. So the derivative is 18x squared. Here's our second rule. We differentiate term by term. So if we get a question like this, find the derivative of 3x to the power of 5, take away 2x cubed plus 6x squared. We're going to do each one of these in turn. Let's have a go at it. The 5 comes down and multiplies by the 3. 15x, drop this power by 1, the power of 4. Take away. The 3 comes down and multiplies by the 2. 3 2s are 6. X, drop this by 1, squared. Plus, the 2 comes down, multiplies by the 6. 12x, drop this power by 1, power is 1. So there's our answer. 15x to the power of 4, take away 6x squared plus 12x. Our third rule is the derivative of ax is a. Now in this case, a is just a constant, like a number, like 2 or 3 or 6. Let's have a look at an example. Find the derivative of y is equal to 6x. Now what we can do is write it as 6x to the power of 1, because that's actually what it is. Now we can use our power rule. The 1 comes down and multiplies by the 6. X. Drop this power by 1, becomes 0. And what is anything to the power of 0? It's 1, isn't it? So that actually just cancels out. It's the same as 6 times 1, which of course is 6. So let's have a look at our rule. The derivative of ax is a, the derivative of 6x is 6. And finally, the derivative of a constant term is 0. Now a constant term doesn't have an x in it. So let's look at an example. Differentiate y is equal to 3. Again, I'm going to do something sneaky. Instead of just writing it as 3, I'm going to write 3x to the naught, because that's the same thing, isn't it? X to the naught is just 1. Now we can use our power rule. The 0 comes down and wipes everything out. It doesn't even matter that this x to the naught is going to become x to the negative 1, because everything is going to be equal to 0. So the derivative of a constant term is 0. Let's look at some examples. All right, we want to find the derivative here. We're going to go term by term. The 5 comes down, multiplies by the 3, 15x to the power of 4 plus, what was this one? Remember, it's just 2. This is a power 1. The 1 comes down, multiplies by the 2, x to the naught, and that one is 0. So our derivative is y dashed is equal to 15x to the power of 4 plus 2. How about this one? Here I've got negative 3x to the power of 4 plus a quarter x. All right, the 4 comes down, negative 12x cubed plus, this is the same as this one. This is x to the power of 1. The 1 will come down, x to the naught. That's just going to be a quarter. So f dashed of x is equal to negative 12x cubed plus 1 quarter. Now you might have been thinking, well, what about negative powers? And we can actually differentiate negative powers using the same method. Let's find the derivative of y equals x to the negative 3. The negative 3 comes down, multiplies by the x, drop this power by 1, becomes negative 4. The derivative is negative 3x to the negative 4. But what if they write the question like this? It doesn't actually have a negative power, it's got an x on the denominator. We need to use our index rules to lift that x up to the numerator. So that's the same as 4x to the negative 1. Now let's differentiate. The negative 1 comes down, multiplies by the 4. X. Drop this power by 1, becomes negative 2. Now we can leave it like that, but there's this unwritten rule in maths that we should leave our answer in the same form as the question. So you can see this doesn't have a negative power in the question. So let's drop this x negative 2 down to the denominator. And there's our answer, negative 4 over x squared. And fractional indices are fine as well. So let's differentiate 2x to the power of 1/3. The third comes down and multiplies by the 2. X. Drop this power by 1. A third take away 1 is negative 2/3. And so we're going to end up with 2/3 x to the power of negative 2/3. How about if we write the question like this? F of x equals the square root of x. We need to turn this into index form first. This is the same as x to the power of a half. Now we can differentiate. The half comes down, x, drop this power by 1 gives us negative a half. And remember that unwritten rule? We're going to turn it back into third form. The negative means it's going to be on the denominator. The half means it's the square root. So our answer is 1 over 2 root x. Now a couple more before I let you go and do some more work and some practice on this. What about brackets? If we want to differentiate expressions inside brackets, then we'll expand them first. So if we want to differentiate this, I'm going to use FOIL, which is going to give me 3x cubed, take 7x, take away 6x squared plus 14. Now don't stop here, you actually haven't done any differentiation. All you've done is some algebra. Now let's differentiate. So it's going to be 9x squared take away 7. Take away 12x plus 0. Okay, you can get to the point where you can do these quite quickly. We are going to be learning a method called the product rule, which is going to help us differentiate products in brackets. And what about quotients? Here we have a top-heavy fraction. Can you see that? 2 terms on the top, 1 term on the denominator. I can split it into 2 fractions. It's going to become 3x over 4x, take away x squared over 4x. And I can simplify that. 3x over 4x, the x's cancel, and I get 3/4. Take away x squared over 4x, one of the x's cancel, I get x over 4. So now I want to work out the derivative of this. Well, the derivative of a constant is 0. Take away, this is a quarter x. Our answer is going to be -1/4. Make sure that makes sense to you. What about this one? We actually can't do this one at this stage. It's a bottom-heavy fraction, and I can't split it up. But we are going to be learning a method called the quotient rule, which will help us differentiate this question. Let's finish off with this. Differentiation is not restricted to y and x. There are many other quantities that we can differentiate. For example, what's this formula? This is the volume of a sphere, isn't it? What happens if we differentiate v with respect to r? Now I should point out we can only differentiate with respect to one variable, and pi in this case is not a variable, it's a constant. It's just a number. So let's work out dv dr. The 4/3 stays, the 3 comes down, multiplies by pi r squared. Tidying it up, the 3's cancel out, and I end up with 4 pi r squared. Do you recognize that formula? It's the surface area of a sphere. Now, why do you think that is? What does this mean? How is the volume changing as the radius is changing? So as the radius is getting slightly bigger, how is the volume changing? Well, it's like it's getting an extra cover all the way on the outside of the sphere, which actually is the surface area of a sphere. So this actually does make sense. Every time that r increases, we get another layer on the outside. So let's summarize what we've found so far. The derivative finds the rate at which some quantity is changing as another quantity is changing. And that can be what is happening to y as x is changing, or what is happening to volume as the radius is changing. Or later on we'll be looking at this. What is happening to x as time is changing? Okay, that'll do us for this lesson. Our next lesson we're going to look at properties of curves.